In this video, we are going to discuss what is a process. So process is the basic entity that denotes a job or a task that runs on a computer. For example, any of the applications that we use on the day-to-day basis, like a web browser or a video game or a simple C, C++ or Java code, all of these actually run as processes on the computer. Let's actually start with taking an example of a C code. Now, as you can see, this is a very simple C program, which is adding two numbers and returning the value of that and printing it out on the console. This is what you call as a program. So what is a program? A program is a set of instructions. Now, what do we mean by instructions over here? Now, as you can see, this code has been written in the C programming language. We have a bunch of other such high-level programming languages like C++, Java, Python. So all of these are actually high-level languages, meaning that they denote what we as humans or programmers can understand and use to write different types of applications. But that is not the kind of language that the computer understands. The computer understands machine language. Therefore, for example, C has its own compiler, which converts this set of instructions to machine code. So basically, the C program is going to be passed into the C compiler, which is going to convert it into machine language. And further, this machine language is now in a format that is executable on the computer, which means that it outputs an executable file. So for example, let's say this C program was stored in a file called code.c. Once it is passed through the C compiler, this is going to be converted into some file, let's say called a.out, which is actually the executable file. And it is in a format that is ready to be executed on the computer. Now the question comes that how is this executable file going to get all of the required resources? Now any code is going to require some memory, CPU, or some other input-output device access, meaning that it needs to execute along with required access to all of the different kinds of resources that are required as per the program written. So coming back, like I said, a program is a set of instructions. Set of instructions that we are referring to here is actually the instructions that are present in the executable file. And now coming to the main crux of this video, which is what is a process? A process is a program in execution, meaning that a program can basically be thought of as some set of instructions that are stored on the disk. But when these instructions get loaded into the memory, when they get allocated necessary resources and the CPU time to actually execute, that is when the program gets converted into process. Each application or each program can be run as different processes at the same time as well. For example, you would have seen that we can open multiple instances of Google Chrome at the same time. Each of that instance basically represents the same program or application code. But when it is executing on the system, it is running as independent processes, each with their own memory, each with their own set of resources allocated. Let's understand how a process is represented within the memory. Now, the code that we saw, that was a set of instructions that was stored in a file within the disk. But when that converts into a process, the first step that needs to happen is to load the program into memory. Memory here means the RAM memory, which is where all of the active processes live. This diagram represents how each process as an entity is represented within the RAM. Towards the lower memory addresses, we have a fixed size of memory that is allocated for the text. Text here basically represents the program, and program is the set of instructions that need to be executed. This text section would actually represent the executable file of the compiled code. And this section has a fixed size because the program file or the executable file also has a fixed size. Okay, so this text section basically stores the set of instructions that need to be executed while the process is running. Then we have a data section in the memory as well. This section is going to store the global variables. These variables are the ones that can be accessed throughout the program. And again, these have a predetermined size because they are actually dependent on the variables that are defined in the program. Therefore, the data section also has a fixed size. Now coming to the interesting part, each process has a heap, and a stack, which are both necessary for the process to execute. So heap is basically for dynamic memory allocation or runtime memory allocation, which is while the program is executing, as in how it requests for new memory, the required memory space will be allocated from the heap. And then there is stack, which is very important for the program execution. Now, as we know, stacks support mainly two operations. There is a push operation and then there is a pop operation. Pushing means pushing something to the top of the stack. Popping means popping the topmost element out of the stack. Now, why it is important for program execution is because let's say we are calling a function in our program. So what will happen? The control will go to the code within the function. Now, after that function has completed its execution, the control now needs to come back to the point from where the function was called. So if you try to understand, there is some state that needs to be maintained so that the control can actually come back. Now the state would include location of the instruction where the control needs to come back. It would need to restore the values of any local variables that were defined at that point or any other such state information. So therefore, whenever a function is called, we basically need to store the current state of the program, including the pointer to the current instruction or the local variables. So this state gets pushed into the stack so that the state of the program can be restored. Now, as you can see, this green area over here, this is actually free memory that has been allocated to the process. This memory is usable by both stack as well as heap. Stack and heap, both of them are expected to grow in size when the program is executing. Heap will grow in size because there can be new memory allocations that are dynamically required. Stack will grow in size because there are states of the process or the function calls stored within the stack. Both of them actually use the same free memory location to achieve this. Heap grows upwards so that it is able to use all the memory over here, and stack grows downwards so that again it is able to use all of the memory that is allocated to the process. There can come a point where, let's say, the heap and stack have grown so much that they end up using all of the free memory that has been allocated to the process. This point is where the program crashes if it still needs more memory to execute. To understand the working of stack and heap better, I have written the C code, which during the course of its execution is expected to use both the stack as well as heap memory spaces. Now, this initially is going to be just a file that is stored on the disk. Let's say code.c is a file that is stored on the disk. This is passed to the C compiler, and the compiler returns a file called a.out, which is actually the executable. Now, this executable is still on the disk, but it is in a format that is ready to be executed on the system. How we can execute it? For example, via the terminal, if you write ./a.out, that essentially starts execution of this C program. At this point, what is happening is this program that was earlier present on the disk gets loaded into the text section of the process. All of this memory is actually present within the RAM. For this particular code example, the data section is actually going to be empty, but let's imagine there was integer, say x equals 10. This integer is actually a global variable, and integers are generally 4 bytes in size. There is going to be a memory worth 4 bytes that is going to be allocated to x within the data section of the program. Now coming to when the program actually starts executing, that is when it is going to require the heap and stack memory locations. Now for the stack data structure, we just saw that push and pop are the two main operations. There is also one more thing, that is the pointer to the top of the stack. As the name suggests, the top pointer basically maintains the address of the top of the stack, because any push or pop operation need to happen from the top of the stack itself. Before we start step-by-step execution of the program, there is one important concept, that is of a program counter or PC. Program counter basically keeps track of the current instruction that is getting executed. Also, keep in mind that whenever a new function is called, we are going to push any arguments of that function plus any memory location that is required, let's say for the local variables defined within that function, plus the return address of the instruction that was the caller of the function. These three things are going to be pushed to the top of the stack so that the state is maintained, and once that function completes its execution, we can use the return address of the function caller to shift the program counter back to the caller of the function, and that is how the program gets executed. Now for any C program, int main is the entry point. This itself is a function. As I said, the functions along with their local variables or parameters are going to be pushed to the top of the stack. So what is going to be at the top of the stack is going to be this main function call, and the top pointer is going to be updated to point to this. Now within this main function, the first thing that is happening is we are calling the function add numbers. So again, this function call gets pushed to the top of the stack along with its parameters and along with the return address to the instruction that called this function. Now this top pointer is going to point to this. Next, what happens within the function? First of all, the program counter will jump over here. The value of a plus b, that is 2 plus 3 equals 5, is computed and is ready to be returned back to the caller of the function. Now, whenever a function completes its execution, we need to pop from the top of the stack. So let me erase this. Now, once this has been popped, the top pointer is again going to come back to this, and the program counter will now point to this instruction. Now here what is happening is we are creating a new array of a predefined size, that is 5, and we are also defining the values within the array. Now because this array has a predefined size, so this array is going to be allocated memory from within the stack. So what is going to happen is this whole array is going to be pushed to the top of the stack, and the top pointer is now going to point to this. Next, what happens? The program counter then moves to this instruction. Over here, again, we are creating a new array, but the difference is we are using the malloc instruction to allocate memory to an integer array of size 5. Now, integers generally require 4 bytes, and we require 5 such integers. So, there is going to be a 20 byte space that is required to be allocated. But whenever we are using such keywords like malloc, or similarly, there are some other keywords as well like calloc. Both of these are used in C. Other examples could be the new keyword that is used in Java. That also behaves in the same manner because all of these keywords basically help dynamically allocate memory within the heap. Now what is going to happen is a contiguous block of memory is going to be allocated for the array 2 within the heap. Now one can ask why the malloc keyword or the new keyword does not allocate memory on the stack itself. Why is heap even required? The reason is over here I have simplified it by providing the size of the array as 5. So even at compile time, it might be possible to know that, okay, there is a 20 byte space that is required to be allocated. But in practice, this value is generally not defined. This could be something that is taken via user input or on the basis of some calculations. Therefore, whenever in code we want to dynamically allocate memory, this allocation happens via these keywords on the heap. Moving forward, the program counter moves to this instruction, which is simply just setting the value of the first element of the array to 20. So that value will be modified over here, somewhere here in the heap. Then the program counter finally moves to the last instruction, which is free. Now free is again a very important function because it frees up any memory that has been allocated to the array 2. So this memory will be freed up, and this is a very important function call. This can help in better memory management of our programs. Finally, we move to the end of the main function, and like we saw, whenever a function ends, we pop any local variables or any stack entries associated with that function from the stack. And since the program has now completed the execution, the stack has become empty. So overall in this video, what we saw is that a process is a program in execution, and a process needs its own set of memory to execute, and we also learned about the different sections of the memory that are allocated to a process. Please let us know in the comment section if these videos were useful for you or if you have any questions. Till then, see you in the next video.